Well, let's take a look. You guys give me a number. All right, good. 7x. Another one. Good job. Plus 3. That sounds great. Let's try another one. Good job. 11.
6.
Plus 6x equals, I don't know, 15. All right. Well, one of these is an expression, and one is an equation. Well, the last unit was expressions, so this one we're looking at equations. Which one of these is an expression, you guys? Yeah? The top one. This one is an expression. Therefore, the bottom one is an equation. So let me ask you this. What's the difference between the two? Yeah?
The equation has an answer?
More specifically, so yes, let's add to that. Yeah?
It has an equal 15.
That is correct. This is the main difference. Equals. Since we have an equal sign, it is what makes it an equation. Expressions do not have equal signs. Nope. It would be helpful also to notice that in an equation we have an expression, but then we have another expression as well. There's two expressions that are equivalent. So if there are things that are equivalent, are there things that are not equivalent? Yes, and we will go over those later. All right, let's look at some additive inverse stuff. Additive inverse is really just asking what we add to something to get 0. So let's say, for example, I'm going to use that color. Let's use this one. What number do you guys want? 8.
3.
Let's make it 28. 28 sounds good.
21.
Well, what would I add to 28 to get 0?
Negative 28.
Negative 28. I'll just make that a negative 28. Okay? So we need 0. If we ever need 0, that's when we use this additive inverse stuff. Let's do another example. Let's say that I had a negative 12. What would I add to negative 12 to get 0?
12.
Yeah, it's a positive 12 right there. Okay? So that became an opposite kind of thing right there. But let's take this a step further and make it an expression. So as you guys know, it is possible to just make that a minus 28 right there. That is the same thing. It's not going to make any difference. But let's say that this was some kind of expression with a variable. I don't know, something like 2x. Okay, what would I add to 2x to make this a 0? I would make that a negative 2x. So if you guys can learn how to do this, which is extremely difficult, all right? If you know how to add something to something else to get 0, then, which is, again, is very difficult, but if you can, then this whole unit will be extremely easy. And unfortunately, this unit is extremely important. It's so important that if you can't do this unit, then the rest of 7th grade, and then 8th grade, and then 9th grade, and every grade after that will be extremely difficult in terms of math, because you'll always be solving equations, which was our objective for today. For this unit, when we look at some examples, we'll see why it's not necessarily important to write plus, a negative, or just write minus. Okay? Because the objective for most of the equations you'll use is to get 0. In fact, we'll be adding 0. So let's look at a different example. This isn't the additive inverse. But let's say that I had a 5x plus 0. Is there a different way to write this expression? Bam, 5x. See how we don't really need the plus 0 because that is the identity property for addition, which gives us just whatever we have. All right. In addition to black type ops, you have inverse type ops. Unfortunately, we don't get to kill zombies here. But, no, it's okay. I mean, what's the inverse of zombies? It's humans. No, don't kill humans, okay? It's very bad. Don't do it. Well, inverse operations kind of undo whatever other operations we're looking at. Now, for this specific purpose, we're not really concerned with addition and subtraction. because that is how we get the additive inverse for 0, okay? So we're just looking at inverse operations for multiplication and division. And what is the inverse operation for multiplication? And division. What is the inverse operation for division? Multiplication, okay? So since we have these, it's nice because if we ever see multiplication, we can inverse it into division. Or if we see division, we can invert that into multiplication. And this is only for multiplication and division. Let's look at an example up in here. So you guys give me a number.
42.
I heard 14. Bam, 14. So what would I do? Now we're just looking at multiplication or division. What would I do to 14 to get 1? I would divide it by 14. There we go. See that? Well, let's try a different one. This one will be extremely difficult. Give me another number. Let's make it a negative 11. What do I got to do to a negative 11 to make that a 1? I would divide it by negative 11. Very good. Well, let's say that, for example, we have some kind of fraction, something like, something you guys like a 1/2, right?
Wait, I thought you were supposed to be getting 0.
That was for the additive inverse stuff. Right now we're looking for inverse ops, which is where we want 1. We want a 1 out of this stuff. So if I have 1/2, 1/2, what are we going to do to 1/2 to make this 1?
Times it by 2.
Yeah, see how that's 1 divided by 2? So the inverse operation is to multiply this by 2. Well, the 2's cancel out and we're left with 1. So this one will take your intelligence to the limit. Let's make this a negative 3/4. What do I got to do to negative 3/4 to make it 1? What I would recommend. See those first two that we did? How we were dividing? Well, what happens when we divide something by itself? We get 1. Anything divided by itself is 1. But this is division of a fraction. What do we do when we divide by fractions, in fact? Yeah, we're going to change it to multiplication, and then we reciprocate the fraction. So that's negative 4/3. You see that? Well, what's negative 3/4 times negative 4/3? 1.
12.
1.
12 negative 12. 12 over 12.
12 over 12, which is
1.
There you go. So as it turns out, for these types of fractions, if you reciprocate them and then multiply, then you will get 1. Again, this is another very essential skill in this unit. If you can get 1 using these inverse operation stuff, then hopefully the rest of it will go extremely smoothly. There's 2 other things we need to remember in these. And that is, if you do something to one side, you must do the same thing to the other side to maintain equality, okay? So let's take a look. So we're going to make the models for these. And then we'll solve for the m there. So what we're trying to do is just figure out what value of m would make this a true statement. So in other words, what number plus 3 is 7? Yes, I understand. Some of you guys can do that in your head. However, on the homework, they want you to show models for these. So if you want credit, you'll have to show a model. Okay? So, on at these. This is the bar models. So we got 2 bars that have the same value. That's why it's equal, you guys. Alright, now 1 bar is represented by the left side of the equal sign, which is just the expression m plus 3. So I'd have an m, and then I'd have a positive 3 right here. And then the other bar just represents a good old-fashioned 7 right here. Now if I want m, see how I've got these 3 right here with the m plus 3? Well, if I chop off 3 from the 7, see, now I have a bar that also represents the m. So if this is 3, then to make this full bar 7, let's get rid of that 7 first. If that's 3 and the whole bar is 7, what is the rest of it? A 4, right there, okay. So, in other words, we can kind of get rid of these 2 3 parts because they match each other. And we just have an m that is also represented by 4. So, our answer, m equals 4. Alright, number 2 is a little bit different because now I've got 2 bars. One represents an 8, and the other represents a k, but a k where we've taken off 2, right? So in other words, to make this a full k, what do I got to tag onto this thing? A 2. So if I do it to 1, then to make it the same, I've got to do it to the other one. See, now instead of this being a k minus 2, by tagging on that other 2, the whole thing now becomes a k value. That's okay. We only needed 2. So, we can see then that a full k value is actually worth how much? Well, we had an 8 right there, then we got this 2. So the full bar again would be 8 and 2, which is 10. K is 10. Alright, again, let's use a good old bar model like these. And then we got the same bar up in here. Well, the first bar is going to be split up into 3. And this is where it's important. It's actually pretty crucial to remember what multiplication is. That's 3 times n, which means we have 3 sets of an n. There's an n, there's an n, and there's an n. Now this other bar represented 18, right? But we're going to split it up into 3 parts so we can know how much just one of the n's is. So what operation would that be? Hold on, I'll get to you in a second. Each of these would be represented by 6, right? So this n is a 6, this n is a 6, and this one 2. So n in this case is equal to 6. Now this one's a little different because we got 17. So let's give ourselves a nice bar right here. This one is represented by 17, but we got another bar that's equal to it. And that's going to be split up by 2 j's. Actually, let me redo that. I got a 1, then I got 2 j's. 2 j's and a 1. So if I split my 17 up right here, this is 1, then how much is the rest of it? 16 right there, you see that? And now what I can do is I can take off that 1 and this one and just compare a smaller size bar, which would be 2 j's and 16 now. So we got 2 j's is 16, so how much is each j worth? 8. So I'm just going to split this up into 2 parts. Each of these bars represents 8, so each j is an 8. Oh, this one's very difficult because now there's a fraction. Here, let's take a look at how this may look otherwise. This is 1/2 of a j is 6. Now here's what you cannot do is say that half of a j is 6, so 6 divided by 2 is 3. No! That would be very bad. That's not what we're doing right here. In the model, here's what we got. I got half of a j right here, which is also represented by 6, right? Well, I want a full j, so how much more of a j do I need? I need another half of a j. So I need 6 more right here. And now this full bar right here represents a j. And this full bar right here represents 12. So each j is equal to 12. Y plus 3 equals -5. Let's take a gander at these. So if I had a y, and then I tagged a 3 more onto that, that's a y, then I would have the value of -5. So what do I got to do on these? Yeah? All right, so here's the problem with this, is that we got those positive 3, and down here, these are all negatives. Down here, negative 1. So I can't just shave off 3 parts of that 5 and say, well, y is negative 2. No, that would be very, very, very bad. So what do I got to do to get just the y is I would have to tag on 3 negatives. You see that? So I would have to tag on 3 negatives right here. Well, then I've got 5 negatives and 3 negatives. And then I would have a y. Y equals negative 8. Now that may not have made a lot of sense. And that's okay. That's just with the model stuff. We will do some algebraic type stuff. But remember, if the homework asks for a model, you must provide one. It may have been easier to solve some or all of the problems above in your head. That's good. That means you're making sense of the problem. But in this section, we're going to focus on the structure of equations and how properties of arithmetic allow us to manipulate equations. Even though the answer is important, in fact, more important right now is that you understand the underpinnings of algebraic manipulations. That's a big word. So let's solve these any way we want. It said we should use a model or words, but we'll just speak it out instead of writing them. So number 8 right here, it's saying if we had 2 of the same value, which is unknown, and we added 1, would give 5. If that were the case, what is the value? 2, right? 2 times 2 plus 1 is 5. Bam, there we go. What about number 9er? 2 times some number plus 1 is 9. So what is the number? 4. 2 times 4 is 8 plus 1 is 9. But then it changes this and make that, excuse me, a negative 9. So 2 times some number plus 1 is negative 9. Then we want to figure out what the number is. So what would that number be? Very good. That now is negative 5 right here. So it says x minus 1 is 6. So what number minus 1 is 6?
7, sorry.
Very good. That would be where x is 7. Now it did say to use a model, and you will have to do that on the homework, but we'll look at some others that are a little bit more helpful for us. What about this one? X minus 3 equals 5. Let's look at this a different way. So let's say you go trick-or-treating right here. There's your bucket. And it's very happy with the thingy, you know what I'm saying? So this represents our x value. Now if we had that and then we said, hey, if I ate 3 pieces of candy, then I really should end up with 5 pieces of candy. 1, 2, 3, 4, 5. Well, if you had in your bucket some candy, then you ate 3 pieces, then you ended up with 5. How many pieces would have been in the bucket?
8. Negative 2.
21. There would have been 8.
Yes, you'd have had to have 8 pieces of candy in the bucket. So 8 is equal to x on this one, okay? Bam. Let's look at this one. Well, if I have 8 pieces of candy, let's do this a little bit different this time. 1, 2, 3, 4, 5, 6, 7, 8. And these would be pieces of candy you have, so they're positive. And this equals 7 pieces of candy. 1, 2, 3, 4, 5, 6, 7. And these are positive as well. So we have 8 positive pieces of candy and 7 positive pieces of candy. But with the 7 pieces, we also include a bucket of positive candy as well. Well, if this were the case, now these have to be the same. So if this were the case, how many pieces of candy would be in the bucket? Now it has to be the same amount of candy on each side, right? Yeah, there would only be 1 piece of candy in the bucket. So we see that m equals 1. Let's use a different model now. So this one is 6 equals 3x. Now, here's what we really like, is we really like monies. So if I had a 6 large gold, solid gold coins that you had right here, right? Everyone likes some good old money. And all 6 of these would be considered to be in 3 bags of coins. So we got 1 bag, we got 2 bags, and we got 3 bags. 3 bags of coins. Now each bag has to have the same amount, right? Each bag, by the way, is representing an X. Well, if this were the case, how many coins would be in each bag? 2, right? We could show that that would be in one of the bags, that's in another bag, bam, that's in another bag. And behold, we have 2 coins in each bag. Bam, nailed it. Well, this one's a little different because here, let's use the money example again. So we got 1, 2, 3, 4, 5, 6, 7, 8. These are all positive. But then over here, we got 2 money bags. But these money bags is different. That was a bad money bag. Oh, that's a good one. Money bags. So we got 2 money bags. But the problem is these ones are negatives. So that's the opposite of the monies in the bag.
Does that mean there are dead bags?
And these are equals. Yeah, so these are dead bags. Yeah, not dirt bags. Okay. Well, in any case, we got these 2 dead bags, and how much dead would be in each of these?
4 dead.
Yeah, that's very good. Each of these would have inside 4 dead coins.
Dead.
No, not dead coins.
Dead. Body.
Debt.
Oh, dead.
4 dead coins. Because it's the debt of a debt, so that's actually a positive, or the opposite of a debt, which would be positive. So each of these, again, represents how much is in each bag. So M equals a -4. Alright, -5 plus 3n equals 7s. Which method do you guys want to use? Bar, candies, or monies? Alright, candies it is. Put it in the basket, please. Basket. Alright. So in this example, we've got 3 candy basket thingies. Or a pillowcase is fine. And over here are 5 pieces of candy that you owe someone else.
You don't just simply owe someone candy.
Oh, here you do, though. This is an alternate math universe. So, here I've got 7 pieces of candy over here that we have, so that's positive. So if you include those 5 pieces of candy that you owe, how much would be in each pillowcase, I guess? Well, here's what we're going to do. This one we're going to do a little bit different. So on this one, I'm going to use what is considered to be the additive inverse property using the models. So I just want the buckets. And yes, we can separate this with some kind of line so we can see the separation of the 2. And right here, how can I get rid of those negative candies that we owe someone's? Yeah, we have to have 5 positive candies. So 1, 2, 3, 4, 5. But remember, we explained this at the beginning of the lesson. If you do it to one side of an equation, you must do it to the other side. So I'm going to add 5 more pieces of candy over here. Well, what this does is it cancels out 1, 2, 3, 4, 5. You guys remember what we call it when we cancel them out like this? 0 pairs. That's very good. So a 0 pair means that we can just cross these out and get rid of them, which is pretty nice actually. So we're going to ignore these. Now we got 3 buckets, and over here what do we got? 2, 4, 6, 8, 10, 12. We got 12 pieces of candy, so how much candy would be in each bucket?
4.
4 pieces of candy. So that would be in a bucket, that's in a bucket, and that's in a bucket. All right, number 18, we got negative 7 equals m minus 9er. So let's use principles of equality, which is what the additive inverse and inverse ops are, because they will maintain equality as long as if we do it to one side, we do it to the other side as well. But on this one, I'm going to show you guys not only algebraically, but also using the models so that you can compare the two and hopefully use the both when you do your homework. All right, so let's look at this. Here we got a negative 7 equals m minus 9er. So over here, using the model, we would have 7 of these negative stuff. 4, 5, 6, 7. All right, so we'll make this bags of coins. So if we do it to one, we're going to do it to the other. And so we got one bag of coin right here. And then we got 9 negatives on this side. 1, 2, 3, 4, 5, 6, 7, 8, and 9er. These are all negative. All right. So we got this set up pretty good. Now, how do I just wanted the bag though, right? I just want to know how much is in the bag. So can I get rid of the coins? Sure, absolutely I can. How do I get rid of coins? I'm going to use the additive inverse. So I'm going to tag on some positives on here. 1 for each, and each of these is positive. But once again, if I do it to one side, I got to do it to the other side as well. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9er. Each of these is positive. All right, so let's see what this does. Well, these are all 0 pairs here on the right. 9 0 pairs there. And then over here, we got 7 0 pairs. And now I can see that one bag would contain how many coins? 2. I got the bag, and then right here, I've got 2 coins. So the m is going to equals 2. All right, so let's look at this algebraically so that you guys can make the connection between the two. So we had the bag and then 9 negative coins. How did we get rid of those 9 negative coins? We added 9 positive coins. Well, what's negative 9 plus 9? That becomes a 0. That's important to notice. But remember, if we did it to one side, we had to do it to the other side as well. And this gives us m equals, what's negative 7 plus 9er? 2. And now we can see that m is 2 using the same operations but without all the drawing and stuff. All right, number 19er. Well, right here. So we're going to do the same thing, and actually it may be helpful for you guys to see this as 12 equals w minus 4. So if I wanted just the w, right? I just want the w equals something. How do I get rid of that minus 4? Yeah, we need to add 4. Because when we add 4, in this case to both sides, that becomes a 0 right there. And w equals 16. Here's the great thing about 20, is that this negative 4k is not being added or subtracted anything. So there's no need for the additive inverse on these. When we split this up, how can I make this, instead of a negative 4k, to be a 1k? Well, yeah, red. Very good. This is the inverse ops stuff. So if I divide both sides by negative 4, then I get that 1k, which now equals 5. But of course, we don't have to write the 1 there. So it just gives us k equals 5. Number 21. Which property are we using? The additive inverse or the inverse ops?
Inverse ops.
We want inverse ops because in this case, we want it to be a 1n. We don't want it to be 0n because it just cancels itself out. So what do we got to do to this to make it a 1n? Alright, so remember that the inverse operations, if we have multiplication, the inverse operation is division. What operation is between the 2 and the n? Multiplication. So what operation should we use to get rid of it? Division, specifically by 2. Because 2 divided by 2 is 1. So negative 18 divided by 2 is negative 9. But of course, we can get rid of that 1 and just say that n equals negative 9.
Wait, so do you always...
So it's important to notice, is there any operations with that negative 18? No. But there is with this 2n, so we can invert operate on that in order to establish our 1n. So we got to look and see where the operation is. But yes, to say it like that is okay. If we divide by the coefficient, which was on the last test, then we will always have our answer. But you got to get the n's by themselves, or sometimes it's x's or m's or some other letter. So 22, additive inverse or inverse ops?
Inverse ops.
Inverse ops, right? So what are we going to do to both sides on this one? Divide by what? Divide by 3. 3 divided by 3 is 1, so we have an x. Negative 15 divided by 3 is negative 5. There it is. Alright, 23. Additive inverse or inverse ops? Inverse ops. So what are we going to do? Multiply or divide? Divide both sides by? Negative 5. So negative 5 divided by negative 5 is 1. So that gives us the 1y, which is what we want. And what's 40 divided by negative 5? Negative 8. So we get y equals negative 8. That's it. Alright. So on this one, again, the main purpose for us to start with is to get the x's by themselves. So in this case, I have negative 2x's. How do I get those 2x's by themselves? I need to subtract this 9 out of there. Because I can't add or subtract anything to it, okay? So if I subtract 9, that's going to give us a 0 pair out of count.
Wouldn't you be...
Alright, so this equals 5 minus 9er is negative 4. Now we can get the coefficient of x to be 1 by dividing both sides by negative 2. So in this case, x equals 2. Alright, so again, we have some addition on those x's, which we don't want. We just want the 4 bags of coins or the 4 sacks of candy. So we can't have those 7 pieces of candy just laying around. How do we get rid of them? Yeah, we eat them, so in this case we would subtract them. But again, if I do it to one side, I got to do it to the other side. So now I've got this 4x, which equals, what's negative 5 minus 7? Negative 2, right? No, it's not negative 2.
It's like negative 13.
It's negative 12.
Positive 12.
Negative 12.
Oh, we're not multiplying.
No, it's not multiplication. Very good. All right, so how do I get an x all by itself? Or to make that a 1x? I got to do something to that 4, right? I'll have to divide it by 4. And I got x equals negative 3. We don't really need that 1 there.
Wait, negative 3?
Negative 12 divided by 4 is negative 3. Negative 8 equals negative 3m plus a 10. So what do we got to do first on this one, you guys? That's correct. Let's get rid of that 10 by subtracting a 10. But if we do it to one side, we got to do it to both sides. We're going to drop this negative 3m. And this equals negative 8 minus 10?
18.
Negative 18. Now how do we get this to be a 1m? What do we got to do to that negative 3? Divide by negative 3. So m now equals 6. What are we going to do foist? Yeah.
Get rid of the 1.
Bam, how do we get rid of that 1?
You subtract
Subtract 1. So that gets the 7 z's all by themselves, because that becomes a 0. And what's 15 minus 1? 14. So what are we going to do now?
Divide, but also when you talk
Divide by what?
divide by 7.
That is correct.
When you talk in your slang words, you sound like one of the newsies from Jersey.
I don't know what a newsie is.
You know, like the movies, Newsies?
Is that like a rookie?
No, it's like
You're new. Sounds like newbie, you know, like
Right?
noob.
What?
Like, welcome to Call of Duty, you're a noob.
Get off. You're on my level.
Yes. You need to play with people of your own caliber. Alright, so in this problem, this is number 4 on the next part. This is x over 3 equals negative 6. Now, it said to use models. I'm not too worried about that right now. We did some of these with, I think, the money bags and the candy stuff. But let's use, in this case, we're looking at inverse ops, not the additive inverse stuff, because there's nothing being added or subtracted. So, what operation is being used with the x and the 3 there? It's division. So how do I get rid of division? Going to multiply it by the 3. See, then the 3's cancel out, and I just have the x, which is what we want. Negative 6 times 3 is negative 18. So it's important to be able to divide and multiply both ways when given problems like these with the equations. No, you like them. Alright, so if this was 1/2 of an x, which equals a 3, what can I do to make this a 1x?
Multiply.
Multiply by what?
2.
2. See, then the 2's cancel out, and I got 1x equals 6. Of course, we don't need the 1 there. So this is x equals 6. Alright, let's look at the model on these. So remember, if we had a full bucket of candies, well, actually, how much of a bucket do we have? Only a half bucket. So, we only have half. But how much is candy is in the bucket? 1, 2, 3. 3 pieces. So if we go back and make this a full bucket,
that means there's going to be 6 pieces.
well, then we got this other half, which would include another 3 pieces. So the full x would be how many pieces? 6. Sorry, I forgot the other part of the handle there. Alright, let's rewrite this one though. Let's make this a 7 plus x halves equals negative 3. Maybe easier or worse for you to see it that way. It doesn't really matter which way you do it. So what do we need to do first to solve for x on a these?
Multiply.
No, we need to get rid of the 7. Excuse me. So we got a 0 pair up in here. And we're just left with the x over 2 equals negative 3 minus 7 is negative 10. Well, how do we get rid of that half? Just multiplying by 2. So that's the inverse op thing. The 2's cancel out and we got x equals negative 20. Alright, let's make up our own because it would be so fun. Let's make this, I don't know, someone give me a number.
50,000.
Alright, 50. And then we'll make this plus,
15.
we'll make it x over 1. 4 sounds good. And we'll make this equal to, what do you guys want? Alright, 20 sounds good. So when we solve for x on a these, what's the first thing we will do? Yeah, let's get rid of the 50. So we got to subtract 50 from both sides. Now we got x over 4 equals negative 30. Very good. Alright, what do we got to do to solve this one, you guys?
You have to
What? Very good. Multiply both of them by 4. So the 4's cancel. We have just the x equals negative 120. That's better. Alright, we're going to use models to solve these first few of these. And then you guys are going to love it because these ones are colorful. Like this one, right? We got n plus 3 equals 7. So on at these, this is the model that they gave us. Notice that the 7, right, we're going to take the 3 off of the 7. So how much is this bar? How much is left in this bar? That's 4. So then we can take out that 7 up in here. And take out the 7.
Is our homework gonna be this easy?
Yeah.
So M's 4.
Alright, so see the 3 we're not concerned about because it matches with that 3. The m right here is matching with this 4. So we can see there that m is 4. Alright, this is number 2. The whole purpose of all of this, yes, is to find the value of the variable. Alright, so on at these, we can see that k minus 2 gives us this, it's kind of like a bar. We can pretend it's like a gold bar. And this gold bar is worth 8. But it's k minus 2, so to get a full k, we're going to have to tag on an extra 2 onto that thing. But if we do it to that one, then we should do it to this one as well. See, now I have a full bar that represents the k value. And since k minus 2 was 8, now that I've added an extra 2 to the 8, I see that k is equal to 10. I like this one because it's supposed to help us remember what multiplication is, and this is 3 times n up in count. So it means that we got 3 n's, or 3 groups of n, which is shown in this box up in here. So it'd be like saying, let's split this up into each part up in count like this. Well, if this full bar was worth 18, how much is each of these parts worth?
6.
6, right? That may seem bad, actually. Well, now I can see that each one of the n's represents its own 6 value. And so I can just write that n equals 6. Alright, number 4 shows that we got 2 j's and a 1 that match that 17. Notice that both bars are always separated by the equal sign. So the 17 is the same as the 2j and the 1. So if we split this up, there's a 1 right here. And then each j. So the 2 bars, right, because we can get rid of this garbage now and focus just on the j parts. Well, if that was worth 17, we took one off, so how much are the 2 bars worth?
16.
Yeah, these 2 are worth 16 each, or just 1. So if we split that in half, which is really what's happening right now, each of them is worth 8. Therefore, we can see that this j is 8, and this j is 8, so j equals 8. Alright, number 5. Here we have half of a j, which means we could rewrite this, by the way. And that rhymes, that's pretty cool. So I got half of a j equals 6. These 2 equations are the same thing. Well, if half a j is 6, well, let me show you guys this using a model. And it should be time appropriate because, it's almost Halloween time. So we got the trick-or-treat thingies, and then they got there's usually some kind of pumpkin face on it.
Whoa, wait, you need to do the bottom of the squiggles.
Alright, it's too much work. Anyways, this pumpkin right here, we're going to cut it straight up in half like these. There we go. You're welcome. Alright, well, half this bucket has how many candies? 6. 1. Let me get rid of that garbage, actually. So the bucket has 1, 2, 3, 4, 5, 6 candies. Well, if I had a full bucket then how many candies would I have? Well, the other half would have the same amount of candies. And we can count these. Let's count them, each one. Bam, 12. J is 12. You see that? So some people get this mixed up. here's what happens, and this is an unfortunate but common mistake, is since j is divided by 2, we think, well, 6 is divided by 2, which would give us 3. That is unfortunate. Poor unfortunate souls. Okay? Alright, let's look at number 6. This one's extremely difficult. Alright, let's take a look at this one then. Alright, let's look at this a different way. Alright? So let's say that this Juan right here,
Oh, I know what way we're doing.
because we really like money. So let's say that we start with this unknown amount. But then you get $3, right? But then you end right here. This is where you will end. You're going to end with this -$5. Well, how much does that mean you started with? You must have started with -$8. Now this isn't really a model, but hopefully it demonstrates a different way to show this game. It may have been easy to solve some or all of the above in your head. That's great. That means you're making sense of the problem. In this section, we're going to focus on the structure of equations and how properties of arithmetic allow us to manipulate equations. Even though the answer is important, more important right now is that you understand the underpinnings of algebraic manipulation. Alright, evaluate. We did some of these on the previous test. It gave us 2x plus 1. Let's evaluate that when x is 3. What do we get? 7. What about 2x plus 1 for x is -2? What? How do you guys get 1? Oh, man. -5. No. -4. Yeah, what the heck? -4, 3. Sorry, that came out wrong. -3, you guys. I'm worried. I'm actually kind of worried now. You're replacing x with -2 and using the order of operations to solve it. Okay. What about 2x plus 1 for x is -3? Alright, now you guys need to be careful. I'm worried you guys are doing this without really thinking about it. What's 2 times -3? -6 plus 1? -5.
See that, Todd? Yeah, I knew that. Next one.
No, let me show you guys why this is important. So that was 2x plus 1. Let's make this 2x plus 1, and then it equals -5. Okay. Could you solve for x?
It's -3.
It's -3, right? Yeah. Well, it's the same thing as though we were evaluating with x being -3. If we know the answer is -5. Okay, so put that on my desk. All right, so if we had 2x plus 1 equals 5, let's use a model again. But we're going to use a different model, okay? So again, I need to separate these so I can tell how the two are equal. And let's use the bars again on these. So we got two bars that have equal value or length, however you want to say it. And right up in here, I've got a 1, and then I've got 2 of these x's, like these. Now it should equal the 5, so I can also separate this up into 5 parts. And this is 1, 1, 1, 1, 1. Now of course the 1's match each other, so in essence they're not really that important either. But now I've got 2 x's that have a value of 4. So if I were to split this up, I can see that this x is 2 and that this x is 2. So we know now that x is 2.
Oh, 2 times.
All right, number 9, I'm going to do this very differently though, okay? So, yeah, I know, that's great. So let's show a model on this. This is a money bag that would be full of monies. But I've got 2 money bags. Each money bag represents an X. And then I've got another coin right here. Now this equals 9 coins. 1, 2, 3, 4, 5, 6, 7, 8, 9er. like these. So I got that 2 x's and the 1. Well, we can see that this one kind of matches that one. I mean, it's kind of like the bar model that we were using. So I've got 2 bags that really represent 8 coins up and down. So how much of the coins, how many coins would be in each bag?
4.
Well, I can separate these 4 and these 4 separately. And each bag would have 4 coins. Each bag is an X, so X is 4. Alright, now this one equals a -9. So you remember that additive inverse stuff? I'm going to use it on this one. So I've got 2 bags once again, like these. And then I've got a coin right here. And then it should equal 9 of these negative coins. 1, 2, 3, 4, 5, 6, 7, 8, 9er. So let me put that right here. And each of these are negatives. Well, I just want to know how much is in each bag, right? So I can't have bags and coins. So I got to get rid of this 1 coin right here. That's no good. I don't want it there. How do I get rid of it? I use the additive inverse. So if I tag on a negative to that thing, you guys remember 0 pairs?
Yeah.
Well, it becomes a 0 pair and it cancels out. But for these, if I do it to one side of the equal sign, I should do it to the other side as well. So I'm going to tag on that negative. And these become a 0 pair. They just kind of disappear up and here. So let's get rid of this garbage too. That's not good. Well, now I have 2 bags and 10 coins, negative coins. So how much would be in each bag? I could split up this one into a bag and this one into a bag. And I can see that for each bag I would have 5 negative coins. Alright, let's consider this equation. X minus 1 equals 6. What value of x makes this equation true? So another way we can look at this, now this is without models.
Wait, why do you have to?
But what value minus 1 would give us 6?
7.
7. Bam. So we know right there that x equals a 7s. What about the equation x minus 3 equals 5? What value of x makes this equation true and justify? So some number minus 3 equals 5. What number minus 3 is 5? 8. Bam, so we know right there that x equals 8. Now these ones are pretty easy to do in our heads, and that's great. The problem is later on, as we make or expand these, it may be a little bit easier to show some work on them, which we'll get into. 8 equals 7 plus some number. What number would we add to 7 to get 8? 1. Bam, we know that m equals a 1. This one's great because they modeled it for us. And we can see that this x represents these two. And all the x's should have the same value, so we can just split this up amongst the 3 x's. When we're splitting stuff up, what operation would we be using? Division, right? So remember how we talked about inverse ops? Well, if I had a 3x equals a 6, and I want this to be 1x, right? Equals something. How do I make that 3 into a 1? Yeah, you divide it by itself. But again, if you do it to one side, you got to do it to the other side as well. So x equals 2 on this, which is shown in the model as well. If I put 1x, it doesn't matter if you put 1x or just x. This one we got to be careful. 8 equals negative 2m. So negative 2 times some number is 8. What would that be? Ty?
Negative 4.
That is correct. We can see right here that it would be m. M would equal negative 4. Well, how do we get that though? So here I've got 8 equals negative 2m, right? But what I want is a solid 1m. So how do I get 1 out of that negative 2m? divided by negative 2. So 8 divided by negative 2 is negative 4. And again, we don't really need the 1 in front of the m, but you can. And we see that m is negative 4. That's all we're doing here. We're solving for each letter. What do we need the coefficient of each letter to be? Well, let's. You guys remember some of the other answers, right? Like m is 8.
Yeah.
Or maybe x was negative 2. What's the coefficient of each of these?
The X and the M.
No, x and m are the unknowns or variables. Yeah?
The number connected to. Oh wait.
Yeah, the coefficient of each of these is 1. It's a phantom 1, you guys. So that's why that inverse operation stuff is so important to remember. What about negative 5 plus 3n equals 7? This one's pretty hard. It's a tougher. Well, negative 5 plus 3 times some number equals 7. What is the number? See, now it's a little bit more difficult to do in our heads. So we got to do it not in our heads. Let's use a model, because it says to draw a model. You guys want the money bags or the bars? Money bags. I like money bags.
No, did they use the Halloween bucket?
Maybe next time. All right, so I got 3 bags of monies, because, well, we like monies. Yeah. And then I got these 3 bags, and then I got 5 negative coins. 1, 2, 3, 4, 5. Each of them being negatives. And this equals 7 positive coins. 1, 2, 3, 4, 5, 6, and a 7. Each of them be positive. Like these. Well, I just wanted the bags by themselves so I can split up the monies, whatever it is, whether they're positive or negatives. So I can't have these negatives right account. That's no good. We don't want those there. So how do we get rid of them?
0 pairs.
0 pairs. That's the additive inverse stuff. So how do I get these to be zeros? We got to tag on some positives up in here. So each of these is a positive. Now how many positives did we put there?
3.
5. So I'm going to put 5 on the other side. 1, 2, 3, 4, 5. And again, each of these is a positive. So what happens to these? Well, this cancels, cancel, cancel, cancel. These are all 0 pairs, which really means that they just kind of disappear. Like these. They go away. That's good. Well, now I've got 3 bags of coins, which is represented by 12 positive coins. So we can see we can divide each bag up, or each of these up into 4 coins for every bag. So we see then that x equals 4.
N equals 4.
Oh, and yeah, thank you.
That works, right?
It was close. I'll take what I can get.
7.
N equals 4, thank you. All right, you guys try this one. Negative 4 equals negative 3m plus 8. Use a model. Models are good. You guys wanted to use candy on this one, right? Yeah! Yeah.
Money bag, money.
All right. So we got 4 pieces of negative candy.
Oh.
Be 21. Savage.
Or you owe it to someone. Either way.
Oh, no.
And this equals
I'm not
to
giving my
3.
candy away.
Yeah, right. We'll see about that, right? We got here's a candy thingy. Got a candy bucket. That's what I was thinking
It's
of.
a Halloween bucket.
3 Halloween buckets, and these are negative buckets though, so these are all negatives. That looks pretty good. A
Hey,
what?
snowman.
A frowny face? Well,
Frosty the snowman.
we're gonna make them on negative here in a moment. So now I've got 8
Halloween time.
of these positives.
You can
It's
skip
not
a
Halloween
holiday.
yet, but it's close.
You can skip a holiday if you really want to.
Yeah, sorry, I forgot the handles on those, but there they are.
Now they just look like
Ooh.
Well, I've got 3 buckets of negative candy, and I've got, well, 8 candies. And on the other side, this is all represented by 4 negative candies, or that you owe someone some candies. So what are we going to do? Well, we want the buckets by themselves, right? So let's go ahead and get rid of these negative candies.
Which ones? Those ones? The 4?
I'm sorry, the positive candies, yeah, the candies that you have. Let's get rid of those so that we just have some 3 negative buckets, right?
How would you get rid
Now,
of
how
them?
many of those negative candies did I tag on right there? 8. So I'm going to need to tag on 8 negatives up in count.
Whatever you did on one side, you have 3.
So each of these cancels out. Each is a 0 pair. That's the additive inverse property. Let's just erase those. Well, now I have 3 negative buckets, and I've got 12 negative candies, right? So if I wanted a positive bucket, which would be great because then it has actual candy in it, how much would a positive bucket have?
They're all... They're 24.
12.
Well, let's look. Let's look. Okay, let's get rid of this. Now I need to make these positive buckets, right? Now you don't have to do it like this. We'll show you different ways, Kate. But the model, hopefully this will make sense.
20.
I need to make these positive buckets.
20.
So you see if I get rid of them all together? All 3 of them? So we just tagged on these 3 positive buckets, right account. But remember, if I do it to one side, got to do it to the other side as well.
The answer.
All right, now we got 3 buckets, but they're positive on the other side, right? Because we want to do positives. But what do I have on the other side? I got nothing. They 0 paired out of there, right? Kind of like our third example, 7x plus negative 7x equals 0. Well, now I've got buckets and candies on the same side, so let's get rid of those candies, right?
No.
Yeah, let's do it. 1. It's all 8 candies.
I'll make
Now I do need them to cancel out, but remember, I just tagged on 8 positive candies to the left side, so what do I got to do to the other side?
8 positive.
8 positive candies, so I'm sorry, that was actually 12.
Adding candy, then erasing it, and then adding candy.
I know, and again, it may not make sense now, but it will, hopefully. It needs to make sense, at least in the future, when we start showing these using principles of equality. Alright, so let's get rid of the candies up and count.
See?
You know, the candies.
New phone. Who's
Add it
this?
to the other side.
Yeah, but it should make sense now, because now
And then add more to the
No,
other
you just
side,
had
and then
10
erase
negatives,
it, and then
negatives,
add more, and erase.
I got 12, right?
Yeah.
Alright, now I got 3 positive buckets and 12 candies.
That's what we started with.
No, we didn't. We had 3 negative buckets. Yeah. X is 4, or M is 4. There's 1 bucket. There's 2 buckets. 3 buckets. Each bucket has 4 candies in it.
You can go through
So
this,
M
you can just do it.
equals 4. Yeah, I know there's better ways to do it, which we'll get into, okay? Alright, let's look at this without models now. So we're going to solve these in what they call algebraic methods, which in this case we will be using properties of equality, which really just is additive inverse and inverse operations like we did before, okay? So on this problem, and some of you guys saw this already, I'm going to mark this like this, okay? I'm going to put a line through the equal sign so that I can perform operations. One of the major things we need to remember, in addition to the additive inverse and inverse operations, is that if I do something to one side of the equal sign, I must do it to the other side so that we maintain equality.
Oh, we're doing the T now.
Now the idea is to figure out what M is, right?
That's why you kept erasing him and putting
Some
it
people
down.
like the 1M. Let me finish. I'll get your question. Now we want this to be 1M. This is already 1M, but it's 1M minus 9. How do I get rid of that 9? Well, let's make it M plus 0. So how do I make that negative 9 a 0?
Divided by times it by.
Now this is the additive inverse stuff, right? So I'm going to have to add 9. But if I do it to one side, got to do the other side. Bam, 2. Now I do have 2 equals M plus 0, but we just don't need the 0. So I got 2 equals M. Bam, that's it. It's actually pretty crucial that it makes sense this way because this is how we're going to have you do it on the test. Okay? All right, here's 23. 40 equals negative 5 times a why. Now what we really want on this, like the inverse operations, right? We want this to be 1y equals something. Doesn't matter what that is. So how do I make a negative 5 a 1?
No. Subtract negative.
All right, now it sounds like some of you guys are focusing on the additive inverse stuff. That's to make it a 0.
We're on 20.
Inverse operations is what's going to make that a 1.
Divided by 5.
So we're going to have to divide this by negative 5.
Negative 5.
But if I do it to one side, I got to do it to both sides.
You skipped 19 to
Oh, we'll get there. What's 40 divided by negative 5?
Negative 8.
So why didn't we add that 5? Because we don't want it to be 0y or 0. We want it to be 1y. Well, 1 is the inverse operation stuff. So what do I got to do to negative 5 to make it a 1? I'll just divide it by itself. Because see, if you added 5y to both sides, you can't even combine 40 and 5y because they're not even like terms. So yeah, if you guys did write it like this without the 1, that's fine as well. Number 19. This one actually is written incorrectly. Let's make this just a simplified expression, w minus 4. That should help us to do this a little bit better. So again, what we want is just a w equals some stuff. So how do I get rid of that minus 4?
Add 4 to it.
Yeah, we need to add 4 to it to make it a 0, right? We could say that's plus 0. But if I do it to one side, I've got to do it to the other side. I get 16. Now we don't need to add 0 in the answer because we just have a w. And we see that 16 is w. It's done. So what would we do on this one, you guys?
K equals 5.
Well, I didn't ask what the answer was. What do we do on this?
Is Bruno Mars talking about math? He says K?
So what do we do on this? Ty? There you go. Why do we divide it by negative 4? Yeah, we want it to be 1k. Again, we don't really need the 1 there. So k actually ends up equaling negative 20 divided by 4. And that is a fiber. If the coefficient of the letter is anything but 1, we're going to have to use the inverse operation property as well. Sometimes we got to mix these up, which I think we got some examples for that too. All right, so this one. Are we using the additive inverse or inverse operations on this?
Inverse.
I have a feeling you guys are guessing.
The other one. Inverse.
Well, there's nothing being added or subtracted, so it has to be inverse operations. So, specifically, what are we going to do to n to make it a 1n? There you go. Just divide it by 2 on both sides. Negative 18 divided by 2 is negative 9er. Do you guys want the 1 there or no?
No.
All right, so let's take it off.
Yes, I actually do.
Too late. Now I have negative 9 equals n. Additive inverse or inverse ops on this one?
Inverse.
Inverse ops. Why? Because nothing's being added or subtracted. So, are we multiplying or dividing up in here? Well, it's being multiplied. So what operation are we going to use?
Inverse.
Which is
Oh.
division. Very good.
That's Bruno.
So what are we dividing both sides by?
3.
3.
3.
And again, 3 divided by 3 is 1. So we just have an x equals negative 5.
Why are you dividing?
Now on this one, again, we just want the x's. So this one, it's okay if we just have a negative 2x. And then we'll take care of it from there. Which means we can't have the addition of the 9. So, how do we get rid of plus 9? Yeah, we're going to have to minus 9. If we do that, then it makes this a 0. It's a 0 pair. And then we got 5 minus 9, which is negative 4. So negative 4 equals negative 2x. So that was the additive inverse property. Now let's use inverse operations by dividing both sides by -2. Because -2 divided by itself is 1. And we get x equals -4 divided by -2 is 2.
How'd you
Again, the idea there is to make that a plus 0, which we don't have to show. We can make it a phantom 0. Because that's the additive identity. 4x plus 7 equals -5. What are we going to do first?
7.
7?
7. What does that mean?
Minus 7.
-7. Very good. But if we do it to one side, we got to do it to both sides. Again, the idea here is to get the x's on their own side of the equal sign. -5 minus 7 is -12. So now I got 4 x's, which represent -12. How am I going to make this a 1x?
How'd you get 12?
Divide it both sides by 4. 4 divided by 4 is 1.
3.
1x. So x equals -3.
How'd you get 12?
Let's look at this problem, but we're not going to use models for this because drawing this using a model would be, that's it, just a little bit difficult. So let's use those principles of equality like we've been doing, which is the additive inverse or inverse ops. So I need the x over 2 to be by itself, but right now it's being added to a 7. So how do I get rid of that 7? I'm going to minus 7. But if I do it to one side, I need to do it to both sides. So the x over 2 drops. And I've got -3 minus 7, which is -10. Now this one is x divided by 2. How do I make this a full x? Yeah, we're going to multiply this. We'll multiply it by 2. And then we got to do it to the other side as well. So the 2's cancel. And I got -10 times 2, which is -20.
Wait, wouldn't you have to divide it?
So it's important to remember this is the inverse operation stuff. Notice that was x divided by 2. So what operation did we use? Multiply by the denominator there, which was 2. So what about this example? Well, I got -3 equals x over 2 plus 2. So again, we want that x over 2 on its own. So how do we get rid of that plus 2?
Minus 2.
Minus 2. But again, if we do it to one side, we should do it to both sides. That's a negative fiber. So -5 equals half of an x. How do we get rid of that half?
Times it by
You have
2.
to add times by 2.
Times it by 2.
Equal -10.
So I got 2 times -5, which is -10. Equals, the 2's cancel out, and we're just left with the x, which is what we wanted. Bam. There's our answer.
The half one.